These are the frequently asked questions for Algebra 2 for section 7.1, where we're going back and talking about some of the things you learned about in exponential algebra. Starting with number 11, it says graph each function. So as I'm looking at number 11, I realize there's no h and k here. This is just graphing the parent function, and the parent function is what I see. So what I have to do is make a table and think about what's going on. Well, what they're raising to the power here, my b value is a 10. So this is going to be exponential growth. I'm not going to need a lot of numbers in the negative range, but I'll just put a few down so that we can see what we would get. So what I need to do is just follow the order of operations. 10 to the negative 2 is 1/100th. So this is going to be 3/100ths when I multiply it by 3. 10 to the negative 1 is 1/10, so we'll get 3/10ths when we multiply that by 3. 10 to the 0 is 1, and 3 times 1 is 3. 10 to the first is 10, and that's already going to give me 30. And I'm well off the grid here, but 10 squared will be 100, so 100 times 3 will give me 300. And this gives me a good idea of what's going on with my graph here. So, with this one, yeah, I'd be tempted to change the scale on this, but I'm just going to go ahead and go with what I have. So at negative 2, we're just a teeny little bit above, and then at negative 1, just a teeny bit more above, and then above the x-axis, and then at 0, we're at 3, and at 1, we're already up at 30. So we can get a really good idea of what this is going to do. Again, it's not going to cross. I should probably make that go up even faster than it is. Not going to cross the x-axis. So maybe like so. Make sure that you put your arrows on there. You know, we do know that this is going left and right forever, but we just need to get a sketch of what that graph is going to look like. And with a 10 for the b value, this is going to be shooting up pretty fast. Number 15, we have 1.5 to the t. And they're just exchanging, you know, a t for the input here instead of the x. Again, you know, with these, sometimes I'll tend to change things into an x and y, and then actually use a fraction instead, because that makes the table a lot easier to do. Again, I do know that 3/2 is going to be growth. That's bigger than 1. So we go ahead and just do a couple of negatives, but spend most of our time thinking about how fast this is going to go up. So if we raise this to the negative 2 power, what it's going to do is it's going to flip it to 2/3, and then it's going to square it, because remember the negative is going to give us the reciprocal. So if we square 2/3, we're going to get 4/9. To the negative 1 power, we just flip it. Negative powers are for reciprocals. Anything to the 0 power is 1. 1 gives us 3/2. Squared, square the numerator and the denominator, so 9/4 or 2 1/4. And then to the 3rd power, then we're just going to raise each of those to the 3rd power. So 3 to the 3rd is 27. So we'll get 27/8. And again, we might want to go ahead and change these into mixed numbers for graphing purposes, or even decimals. And because this isn't going up really, really fast, you know, we might want to pick 4. We might just want to do something dramatic and, you know, maybe go to 8 or 9 and see what we get. But to the 4th power here, we'll have 3 to the 4th, which is 81. And then 2 to the 4th is 16. And, you know, we can do the division there and figure out how much we're going to have. So if we take 81 and divide it by 16, we're going to get 5.0625. So it's going to go in there 5 times, because of course 16 times 5 is 80. So 5 1/5. And we're getting a good read now for the gradual increase of this graph. So negative 2, 4/9. And my smartboard is graphing a little high again. -2, 4/9 about there. -1, 2/3, we'll try there. 0, 1. 1, 1.5. 2, 2 1/4. 3, 3 3/8. And 4, 5 1/5. That's a pretty good look at what's going on, and then we'll connect that all up. Remembering that as we go to the left here, that will never cross the x-axis. The x-axis is an asymptote for that graph. Then number 17, I will come back over here and make some room for that one. Now, number 17, things just don't look right, you know. We are supposed to have a times b to the x, and now we've got this 2x up here. Well, I would say, no we don't. You know, we don't want that 2 there. So, if we realize that this is the same thing as 2 squared to the x power, we can just write this as y equals 4 to the x, and it becomes a lot easier to work with, and it is equivalent to what we had. Again, we can start with a few negatives, but we really care more about what's happening, how quickly this is going up for growth, because we know that that 4 is going to give us growth. So 4 to the -2nd power will be 1/16, to the -1 power will be 1/4, to the 0 power is 1, the first power is 4, and to the second power is 16. So -2 and just a little ways up. And again, my smartboard is graphing a little high. Something along those lines, and again, never crossing that x-axis. All right, on the next page, it says, without graphing, determine whether the function represents exponential growth or exponential decay, and find the y-intercept. So for number 19, I'm looking at what is it they're raising to the power there, and that's 65/100ths. So this is going to be decay, because growth. All right, next part that we need to go after here is talking about the intercept. Reminder that our y-intercept comes from making x equal to 0. And as we go through the notes, we're talking about how that's always going to be 0a, but I'm going to go ahead and put you through this anyway. If we put a 0 in here, anything to the 0 power is 1, and 1 times 2, which is our a value in this case, is going to give us 0a. So that intercept is going to be 0, 2. Then in number 21, we take a look at the fact that our b value right there is 1/8. Again, that is a number that is below 1. So this is going to be decay, exponential decay. And then it always goes through 0a. And our a in this particular problem is 0.8. So those are things that we notice as we go through and do our graphing each time. Next problem is number 27, which is write an exponential function to model each situation and find each amount after the specified time. We've got a population of 120,000 that grows 1.2% each year. So I need to go ahead and change that into a decimal if I'm going to use that in any math formula. And it says it's going to happen for 15 years. So for number 27, my a value, my initial value is 120,000. But now I have to think about that growth factor because I'm keeping 100% and then I'm adding that 1.2% each year, t. So when we simplify this, this will be 120,000, 1.012 to the t. And now if we want to know about 15 years, all we have to do is put a 15 in for t. And then we either follow the order of operations and punch in 1.012 to the 15th power times 120,000, or just go ahead and punch it into the calculator as is. It's 143,512, and I was going to give it a label, but it's just population. So a population of 120,000, we don't know a population of what. we can't give it a label. We have to stop right there. Number 29 is talking about basketball. So before a basketball game, a referee noticed that the ball seemed underinflated. She dropped it from 6 feet and measured the first bounce as 36 inches and the second bounce as 18 inches, and I see a problem. Initially, they're talking about this in feet, and then they change it to inches. Well, 6 feet, 6 times 12 will give you 72 inches. And then the next bounce was 36 inches. And the next bounce was 18 inches, and we can see this is going down by a half. So it started at 72 inches, but each time it's bounced, it is going down half as much. And then write an exponential function to model the height of the ball. Well, x will be how many bounces this thing is going to take. So there's A. And then B says how high was the ball on its fifth bounce. So you would find 72 times 1/2 to the fifth power. And that comes out to be 2.25 inches. Next problem, number 30. Your friend invested $1,000 in an account that pays 6% annual interest. How much interest will your friend have after her college graduation in 4 years? Well, she's starting with $1,000, and it's going up by 6%, but again, you're keeping that initial 100%, and that's a 1, but you have to change that 6% into a decimal. So y equals 1,000 times 1.06. Remember, when you're changing percents into decimals, you have to move the decimal place over 2 positions. And then what we want to do here is find this after 4 years. So what you do is go ahead and put a 4 into it. So I guess it wasn't a part A and B in this one, they're just letting us go. And if you punch that in, we want dollars and cents because this is money after all. So $1,262. And how much do we have in cents here? 48 cents. And there it is. So, they have bullets here to lead you through it. Is an exponential model reasonable for this situation? Yeah, any interest situation, we want to use that. And then setting up that equation, remembering to move those decimals as you go through it. Then, number 32, the population of a certain animal species decreases at a rate of 3.5% per year. So you have that 100%, but you have to subtract that 3.5% each year. So this is not growth, this is going to be decay. So the figure we're going to get for that growth rate is actually a decay rate, which is 96.5%. We've got 100%, and we're going to subtract that little 3.5%. So what we need to do next is think, okay, well, how does that set up? It says you've counted 80 of the animals in the habitat that you are studying. So starting off with 80, but then we have to change that percentage that we found back into a decimal. And since this is going to happen each year, I'm going to go ahead and use t instead of x there. It doesn't make any difference. I mean, we could make this a little fancy and come over here and say that what we're going to find is the population of a function, that function based on t, where t is the number of years. And I'm going to go ahead and do that because I just read part A, and it says write a function that models the change in the animal population. So with function notation, we have that all set to go. And then what we want to do is for B, it says graph the function. Estimate the number of years until the population first drops below 15 animals. So what we would do is we would go ahead and probably put this one in the graphing calculator. The rest of these we were doing were exponential growth. And if it's in the graphing calculator, then we absolutely could find the spot where it's going to drop below 15 animals. So we go ahead and get our exponential decay on the graph, and then we would want to know when it's going to drop below 15 animals. So we could make 15 y sub 2 and make 80 times 0.965 our y sub 1 equation, and then actually calculate the intersection with second trace. And that comes to be up to be about 47 years when we do that. And my new color calculator on my computer has not been working very well, so I wasn't going to attempt that. Hopefully with this explanation of using 15 for y sub 2 and 80 times 0.965 to the t, you can get that. 34, for these it says for each annual rate of change, find the corresponding growth or decay factor. So growth factor is 1 plus r, where r is the percentage as a decimal, and decay is 1 minus r, where r represents our percentage as a decimal there. So in number 34, we had 100%, and now we're going to add 70% to that. So that'll be 1 plus 0.7, which will give us 1.7 as the growth rate for number 34. So really we're just finding the number that we would need to use for b in our functions. And then if we had 100% and it was being subtracted by 75%, well now we're at 100% minus 0.75. You can think of that one as money. So you're going to be keeping only 25% or 0.25. And again, that's what we would use for our b value as we go through there. So growth are the ones up here that you see with pluses, and then decay are the minuses. 46, which function represents the value after X years of a new delivery van that costs $25,000 but depreciates at a rate of 15% each year? So we take our 100% and we have to subtract that 0.15, 15% is a decimal. So we're going to see a b value of 0.85, and there's only one of them up here that has a b value of 0.85. And then of course, we'd look and see, hey, there's 3 of them that have the 25,000 to start with, but this is the only one that's going to give us that depreciation of 15% because it's keeping 85% of its value. So you can kind of reason your way through that one. Then number 48 says, what is the simplified form of 2 plus I over 2 minus I? I wanted to remind you that you can set your graphing calculators now for complex numbers, and you could just punch this in, or hopefully you do remember how to go ahead and do this with the conjugate. So our denominator down there of 2 minus I, the conjugate would be 2 plus I, and when we do first times first and last times last, we're going to get 4 minus I squared, which is 4 minus a negative 1, which is of course 5. And then on the top, you go ahead and do your FOIL up there, and you would get 4, and then outside times outside and inside times inside would be 2I. Last times last would be plus I squared. Well, that's going to be 4 plus 4I minus 1, which is 3 plus 4I over 5, which is answer D. But again, my huge reminder here is we can go under mode and we can set our calculators to complex numbers, and our calculator will do that for us. And that's the end of the FAQ.